get started. Welcome to the first lecture of this semester, and it is the 99th semester of our offering of What Physicists Do. So we're very close to our 100th mark, looking forward to that next semester. When it comes to our speakers this semester, you will find them listed on the What Physicists Do webpage, so you can see who's coming up. As for our speaker today, our very first speaker of the semester, when we ask our speakers what would they like to say to the audience, what would they like us to introduce in their background, you'll often find them listing many different universities, and sometimes they're really proud of them, and you'll hear them, oh, I went to Stanford, I went to Caltech, I went to Berkeley, I went to MIT. But our speaker today has also been to a university that you might have heard of. Our speaker today is from Sonoma State, and whether that's a good or a bad thing, I will leave you to judge for yourselves based upon the quality of his presentation. So no pressure whatsoever. We're very pleased to welcome back Kevin John, who graduated from Sonoma State University's Physics and Astronomy Department in 2007, had 10 years of employment on campus in the NASA EPO group, and recently entered the real world, I guess. So we're very much looking forward to hearing about what you have to tell us, and let's give a warm welcome to our own Kevin John.
Okay, thanks, Tom. So my name is Kevin John. It's a pleasure and an honor to be back here at Sonoma State. Today I'm going to be talking about embedded systems and how I've used them to solve various problems in both industry and in education. I'm going to start with a little bit about my background and my career history with embedded systems. Then I'm going to move on to talking about some of the technical details of the embedded systems that I most commonly use. And finally, I'm going to talk about some of the actual project that I've done with these embedded systems and the problems I've tried to solve. Okay. So I'll go right into my career history. The year was 2007, and this goofy character here was getting his physics degree here at Sonoma State. Most of the computing that I'd done during my coursework for both physics and math had been with Wolfram Mathematica. And I had taken one course that was part of the physics major here, the Physics 380 I think it was, which was programming for physicists. And that taught me a little bit of C and C++. I didn't do anything with embedded systems yet. I knew I liked coding in both C and C++. So I guess you could say I was a real sea wolf. Okay. So after graduating, I started working here at Sonoma State for Dr. Lynn Kaminsky's group, the NASA Education and Public Outreach. When I first started working there, I did a lot of web development programming. I made some applets and some online tools in support of some high-energy astrophysics missions. And then later on, the group started to branch out and do a little bit more in the realm of hardware projects. And I'll be talking about some of those later in the talk. I remained at the EPO group until 2017. My responsibilities, as they were relevant to embedded systems, were mostly in writing firmware, doing some of the PCB design of the hardware, and of course, the cardinal virtue for any engineer, writing lots of documentation. Sidebar for all you future engineers out there. Writing good documentation is usually the difference between code that gets thrown away and code that gets used for a long time. So also in my role at Sonoma State, I was something of a Linux sysadmin. I learned a lot about managing Linux systems, and that's information that's been invaluable to me as an embedded developer, since there's a whole lot of Linux involved in that industry. The job I work at now is at a company called Census Networks in Berkeley, where I'm a senior hardware engineer. The company manufactures traffic detection equipment, so we make sensors and radios and repeaters that go into the roads and help us detect cars to do things like traffic detection and monitoring, and for red light cameras and triggering green lights and that kind of stuff. My responsibilities there revolve mostly around maintaining and designing these systems and computers that do the testing of the hardware before we ship it. So I work in the manufacturing department. And in that job, I write a lot of Python code, I write a good amount of C code, and I do a little bit of PCB manufacturing as needed. I'm also the Arduino instructor at a Santa Rosa nonprofit called 180 Studios. It's a makerspace. We've got a lot of cool facilities with 3D printers and lasers and a ShopBot CNC machine and a wood shop and a metal shop and all kinds of stuff. And I spend the occasional weekend there doing Arduino workshops for the general public. So moving along, I'm going to be talking a little bit about embedded systems and what exactly I mean when I say embedded systems. So to try to pin that down, an embedded system is the two devices that I have shown here are the ones that I use most commonly, the Arduino and the Raspberry Pi. Embedded systems are usually physically small, like the Raspberry Pi is about the size of a credit card, the Arduino is just a little bit smaller. Most of the embedded systems are designed to be single use instead of general purpose. So a computer might have all kinds of uses. You use it for email, web, programming, games, whatever. But usually an embedded system is going to be single purpose. It's going to be designed to just do one thing and do it well. Usually the costs are much, much lower than you'd see with a traditional laptop or desktop machine. The power requirements are usually considerably lower than with a laptop or desktop machine. And many embedded applications are examples of machine-to-machine communication. So they don't have hardware, they don't have input devices, they don't have mice or screens or mice or keyboard, that kind of stuff. They're just machines talking to other machines. And most often these processors are embedded, hence the name, within a larger system that has other devices they're communicating with or other processes that are involved. So I'd like to take a moment to say why I think now is an exciting time to be an embedded device developer. Depending on what you need, embedded devices can range from a few dollars to a few tens of dollars. They're very cheap. Pictured here, I've got that got cut, but the Arduino Nano on the far right, that's $5. There's the Arduino Uno there, it's about $18. There's actually a bigger one for the Arduino family, that's the Mega, that's like $28. And then here's the Raspberry Pi at $35. Aside from the devices themselves being fairly inexpensive, the devices that you might buy to integrate them with are also fairly inexpensive. So companies like SparkFun and Adafruit make products that are available for a few dollars that can talk to these devices and do interesting things. And then even the tools that you need to work with these kinds of devices, like soldering irons and breadboards and jumper pins and that kind of stuff, are all cheaply available. I buy a lot of stuff off Amazon. I know that's not particularly fashionable at the moment, but they've got a lot of cheap stuff, and they've got a really cheap line of Arduino clones called Elegoo that are just as good as the name brand, I think. Aside from the physical tools being cheap and easy to get, the software tools that you need to do this kind of development are also very cheap and easy to get. There's PCB design tools like KiCad that's pictured here that are completely free and open source. There's also tools that are more popularly used in industry like EagleCAD that they're pay, but you can get free open source versions, free not open source, but free versions that are suited to non-commercial applications like for students and such. There's also free tools like the Arduino IDE, the Integrated Development Environment, which is a tool that helps you take the code that you've written and get it onto the Arduino without having to understand too much about how the compilation process works or how the AVR process takes the code that you've written on your computer and moves it to the Arduino. Arduino also has a web-based editor that I hear is good but I haven't used, and they just released a pro version of their IDE that I'm looking forward to taking a look at. Aside from the tools that you use being open source, so are the languages that you program in. So both C and Python, which is for the Raspberry Pi, and C for the Arduino, they're free and open source and really easy to get. And the hardware requirements to run these kinds of programs are really modest. You're going to have a hard time finding any computer today that can't run things like EagleCAD or run things like the Arduino IDE, which isn't the case with a lot of other types of programming or engineering, like if you're doing mechanical engineering and CAD work, those kinds of computers have pretty heavy requirements. And finally, thanks to the internet, there are many organizations that support embedded development within the larger maker community. So there's the Arduino and Raspberry Pi foundations, and they have websites that are good repositories of knowledge where you can go ask questions and have experienced engineers answer those questions for you if you're stuck on something. There's, of course, Stack Overflow, the glorious central repository of all programming knowledge, and if you're a programmer, you use Stack Overflow. And then there's SparkFun and Adafruit, which make parts into breakout boards. And a breakout board is a useful thing if you're doing any kind of rapid prototyping. So a manufacturer might make a surface mount light sensor of some kind. That would be difficult for the average person to work with because it would require them to make a PCB and know how to do surface mount soldering. But these companies will take a sensor like that, they'll pair it with a few other needed components like maybe some resistors or some diodes or something along those lines. They'll lay it out on a PCB, they'll manufacture them and sell them for like $5 or something along those lines. When they do this, they'll also typically do some good library support, so when you buy the part from them, you know that you're going to have a library that Arduino can use to talk to it. And there's also usually some pretty good documentation about how to wire these things up and use them. And by the way, none of these companies are paying me for advertising space. So the last reason that I want to touch on about why it's a good time to be an embedded device developer is that the development times are really fast. So when you're using rapid prototyping techniques like the solderless breadboards and like the breakout boards that I've been talking about, these new devices can be designed and built into a prototype of some kind very quickly without the need to wait for revisions to a PCB. If and when you're ready to lay out a prototype on a PCB, then turnaround times are insanely fast right now, on the order of a few days, and the costs are really low. Usually when I order any kind of PCBs from the houses that manufacture them in China, I spend more on shipping than I do on the boards themselves. So they're a couple dollars. In previous decades, this kind of capability was something that you'd only find in big companies that were multi-million dollars and had big engineering departments with R&D budgets. And so now it's really exciting because the average Joe can do this in their garage for very little money with very little experience. So moving on, we're going to look at two embedded platforms that I use very regularly. They're also probably the most popular platforms in the market right now, and they are the Arduino and the Raspberry Pi. So the Arduino and Raspberry Pi are two different classes of embedded device. The Raspberry Pi is an SBC, or a single board computer. So this means it's effectively a scaled down version of the kind of hardware you'd expect to find in any kind of laptop or desktop machine. It'd be modest by comparison, but all the basic parts are still there. Whereas the Arduino is a microcontroller, or an MCU, not to be confused with the Marvel one. This means it's a vastly simpler device than an SBC, and that can have various disadvantages and advantages. So more sophistication in a device means more complexity, and that isn't necessarily a good thing. The Arduino uses an Atmel reduced instruction set computer processor, or commonly referred to as RISC. And it's a processor that's designed for simplicity, whereas the Arduino uses a advanced RISC machine, or ARM, processor that's designed for mobile devices. I think it's kind of ironic to have an advanced reduced instruction set computer, but that's just me. But these are really popular devices. They're used in all kinds of phones and tablets and stuff. So the Arduino has a 16 megahertz processor, and the Raspberry Pi has a 1.5 gigahertz processor. So it's about 100 times as fast. And on top of that, it has 4 cores versus the Arduino's 1. So in terms of processing power, the Raspberry Pi wins hands down. The Arduino has 32 kilobits of non-volatile memory. And this is memory that doesn't maintain its state, that does maintain its state when the device loses power. So it's kind of like a hard drive for the device. And then the Raspberry Pi uses an SD card for its memory storage, so it has as much memory as you choose to buy for it. But typically these days I don't see a whole lot of cards that are smaller than 16 gigabytes, so that's the number I'm putting in there. So with those numbers, the Raspberry Pi has about 500,000 times more onboard storage than the Arduino does. The Arduino has 3 kilobytes of volatile memory, and the trade-off between the volatile and the non-volatile memory is that volatile memory is typically very fast, non-volatile memory is typically very slow. But of course, when you turn off the computer, or the board in this case, you lose the volatile memory, and you don't lose the non-volatile memory. So the Arduino's got 3 kilobytes of the volatile memory, and the nicest model of the latest Raspberry Pi, the Raspberry Pi 4, has 4 gigabytes. So it's got about 1 million times more RAM. So if we were to compare the processing powers here, it would look like the Raspberry Pi is just hands down a lot better than the Arduino. But as we're going to see moving forward here, things are a little bit more nuanced than that. Okay, so if we were to try to compare these devices in terms of their processing power to consumer devices, we'd find that the Arduino has about as much processing power as this late model Apple laptop, which I'm sure everyone's clamoring for these days. And if we were to look at a consumer device that's comparable to the Raspberry Pi, then we're looking at this Samsung Galaxy S6, which actually uses the exact same processor that the Raspberry Pi does. So moving along, we often care about, with embedded devices, what sorts of other devices this can talk to. And here's a list of some of the interfaces that are useful and which boards have which ones. So the first two, I2C, or integrated circuit, and SPI, those are both two very commonly used serial interfaces that let you talk to low-level components, and both of these boards support both of those. We also care about pulse width modulation, or PWM, and that's a tool that's used for usually with controlling motor controllers or LED, those really popular NeoPixel LED strings that are controlled with PWM. They both have PWM. They also both have UART, which is Universal Asynchronous Receive and Transmit, and that's a hardware serial interface that's very useful for talking at high speeds and with high reliability to computers. The UART interface is actually how you program the Arduino. The Arduino doesn't have networking, so there's no onboard Wi-Fi, there's no onboard Ethernet, whereas the Raspberry Pi definitely has both of those, and also Bluetooth. So the Raspberry Pi is much better suited for networking applications. And the Raspberry Pi has inputs for a mouse and a keyboard and screen, so you can use it like a regular computer. Programming the Raspberry Pi, you can either do it just by attaching interface devices like the keyboard, screen, and mouse, or you can do it over the network with tools like a SSH or with BNC. So, I often hear that the Raspberry Pi and the Arduino are comparably priced, and if you look at just $18 versus $35, there's an argument to be made there that they're in the same ballpark. But if you dig a little bit deeper, you'll find that the Arduino comes with pretty much everything you need to be able to use it, whereas the Raspberry Pi, there's some peripherals for it that are really necessary if you want to get anything done. And then the Arduinos are still coming down in price. I did a What Physicists Do talk about 5 years ago, and at that point Arduinos were $28. Now they're down to $18, so dropping pretty quickly. And then the Raspberry Pi doesn't come with a power adapter, doesn't come with onboard memory, and both of those are absolutely necessary to get it to actually do anything other than be a paperweight. So the real cost of the Arduino is $18, and the real cost of the Raspberry Pi is probably about $57. If you want to use the Raspberry Pi as a full-blown computer, you're probably also buying a case for it and some HDMI cables and a few other things, so then the cost probably gets closer to about $100 or so, which is still a very, very good price for a computer, don't get me wrong. Let's look at the programming languages we use to program these two types of boards. So the Arduino is actually programmed in a language called processing, which is a subset of both C and C++. But if you're working with Arduino, most of the time people are going to be writing the Arduino code in language that's totally indistinguishable from C. So for the purposes of this talk, I'm just going to be calling it C. Both the Arduino and the Raspberry Pi will run C code, but typically when you work with Raspberry Pi code, you're working with Python. All of the documentation that's out there is written in Python. All the tutorials and examples you'll find will be in Python. So if you're looking into Raspberry Pi, you're probably best off keeping in Python unless you're just ridiculously competent at C already. So Python is an object-oriented language, which means that when you develop Python code, it involves creating classes and models, while C is a procedural programming language, so it involves an ordered list of instructions. C is a low-level language, where Python is a high-level language, and that's a commonly misunderstood term. So when I talk about low and high-level code, I'm not talking about complexity, I'm not talking about how difficult the code is, although typically industry would accept that low-level code is a bit more esoteric and harder to write. What I'm talking about is the level of abstraction in the code. So abstraction describes how far away you are from the nuts and bolts of how a computer actually operates. The desktop is a really good example, although it's kind of hidden behind the presentation right now, but we're all familiar with them. So at some level, we all know that there's no files in a computer, there's no directories, it's all just bits and bytes being written to a hard drive. So the part of the code that deals with the abstraction that makes the computer make sense to us as humans would be the high-level code, and the part of the code that's closer to the nuts and bolts operations of how things get written to and read from the memory, that would be the low-level operations. Moving along, C is compiled code, which means that when you write C code, you take some human-readable code, and it's human-readable even if you're not familiar with C, and it might be confusing to you at first, but trust me, humans can read C code. It gets compiled down into hex code, which is just letters, and trust me, no one can read hex code except for machines. So we compile that code, we load it onto the machine, and then we can run it, and it does something. Whereas Python's interpreted code, which means that we don't pre-compile it before we want to use it, we just start it up, and the computer interprets it and compiles on the fly. C is a strongly typed language, and that doesn't mean that when you're writing C code, you pound on the keyboard really hard. That means that when you allocate memory for variables in C, that's a permanent allocation, you can't change it. Whereas Python is dynamically typed, so when you allocate memory for variables in Python, you can come back later and say, no, wait, I want this to be something else instead. And let's compare some general trends about the kinds of applications that these different boards are suited for. So Arduino has excellent device library support. And what that means is that when manufacturers build new sensors, new devices, new motor controllers, they typically look to the Arduino and they want to support the community that uses it. So the makers of the devices will release libraries that are written in C. They'll release some documentation about how to use them with Arduinos. So you've got a lot of more industry support when you use the Arduinos, typically. Raspberry Pi runs Linux, and it has a full and robust set of tools that make it easy to connect and communicate with various networks. So like I mentioned before, it has the built-in Wi-Fi, the built-in Bluetooth, the built-in Ethernet connection. And that makes it a very good tool for doing any kind of networking application. The Arduino, with its 16 megahertz little processor, is far more power efficient than the Raspberry Pi is. And so it's good for battery-powered applications, including it's pretty popular with wearable electronics, if anyone's interested in those. The Raspberry Pi has a mouse, a keyboard, a monitor, and some camera options. So it's great for any kind of human interface device. And then the Arduino is very much geared towards single-purpose applications. When you power up the Arduino, it goes right into running your code. Doesn't give you any options to change that. Whereas the Raspberry Pi boots up and it's a full operating system. It can handle multitasking approaches. So in summary, selecting an embedded platform is a little like selecting a coordinate system when you're trying to solve a math problem. Some problems are really easily solved in Cartesian. Some problems are really easily solved in polar. But they can both be solved, or all problems can be solved in any coordinate system. But sometimes when you select the right coordinate system, it makes things a lot easier for you. Okay, so we've covered some basics about embedded systems. Let's look at some actual applications of problem solving with embedded systems. Excuse me. So the first project I want to look at was called S4, Small Satellites for Secondary Students. This is a project from way back in 2013 to 2015 or so. The problem we were trying to solve here was that we wanted to build a device that could do live telemetry from high-powered rockets in flight, preferably something students would build themselves instead of buying off the shelf. This was the first project I did professionally that used the Arduino. It flew on high-powered rockets in the Black Rock Desert in Nevada, same desert where Burning Man is, as well as a few other launch sites and from some tethered balloons. Oftentimes with embedded development, I find that devices follow some general patterns. So in this case, this is an example of a data logger device where it's got some suite of sensors. It's just constantly polling those sensors, getting the data, and then writing that data to some memory, in this case an SD card. So it had a few components on board. The Arduino is actually in back. You can't see it in this picture, which is a little blurrier than I thought, but oh well. On the upper right-hand side there, there's a barrel jack adapter. That's a connector for the battery. This is powered off of just a 9-volt battery, which gave it hours of battery life at least. There's a temperature, pressure, and humidity sensor there near the top. A 3-axis magnetometer, 3-axis accelerometer. It's got GPS on board. There's a Wi-Fi device there. That's that big red one in the middle. There's a logic level converter. A lot of the, actually most of the sensors on here expected 3.3 volt logic, and the Arduino did 5, so we had to have that converter to switch between them. There's a heat sink there in the middle to dissipate some extra heat. And then the big green thing in the background is kind of the motherboard. That's an example of a printed circuit board, and that provided both electrical connections between the devices so they can communicate, and it also provided the kind of the physical mechanical connection to hold it all together. So it was one solid unit. Now this device had a few of the onboard devices that were SPI and a few of them that were I2C, so we got a good mix of the different options for serial. So this guy had onboard Wi-Fi, which was useful for a few different reasons. First off, it was cool to get live telemetry from it. That's always exciting for the students to see. Second, it was useful in the event that rockets came down at less than optimal speeds and didn't survive, because we could still get some data from them from the flight, even though they smashed and crashed and exploded. And then it was also really useful to be able to see that you were getting data from the rocket when it's sitting on the pad and you have to decide whether or not to launch it. It's always better to have that, assurance that yes, you're getting live data right now. Push the button. Cool. I scroll down. All right. So this was the first instance of a project that I worked on that had a printed circuit board. I'm not the one who designed it. That was done by another famous Kevin from Sonoma State history. So when designing this, though, I learned about the process of having a PCB manufactured. And that is a process where you start with an idea. You take that idea and you build a schematic. You take that schematic and you build a layout that actually shows the physical traces as it goes through the board. You take that layout and you build some design files that get transferred to a PCB manufacturer. And then at the end of the process, they ship you the product and hopefully it works. We also learned from this project some important lessons about maintaining a supply line. So for instance, the GPS that was on board got deprecated about halfway through the project, and we had to switch to a new GPS, which took time and energy. There were some pinouts for some of the breakout boards, those little red ones, that got changed, and we learned an important lesson that the companies that manufacture these breakout boards don't really feel particularly beholden to their decisions from previous incarnations, so they'll freely just decide to switch around, and a pin that was power before becomes data now or something along those lines. And when that happened, we had to redesign the entire board that's underneath, because those traces can't be changed. So there was a whole bunch of boards we had to throw away that were useless because they were designed for an old part. Yeah, that's it about that. And then here is an image of some of the data from S4, where you can see kind of at the bottom there's a big cluster as the device is on and they're milling around about the pad, walking out to the pad, getting lots of data that whole time. The kind of spaced out dots there, that's the rocket going up, and of course it's going really fast, so you don't get as many points along the way. And then there's it coming down, undershoot, and all the data that it got while it was coming back down to the Earth.
Okay.
Yeah.
Is that like projected on Google Earth, like
Yeah.
importing the telemetry data and GPS?
Yeah, yes, we take the telemetry data, we put it into a KML file, and we get the three-dimensional GPS stuff, and then this isn't showing any of the. You can do things like have a heat map that shows you how the pressure changes or whenever changes over time, but this was just where the data was collected. So moving on to another EPO group project. This was learning by making. This was one of our bigger hardware projects that was more challenging. And in this project, we needed an embedded device executing a language called MicroLogo that was developed in-house. That could be used in CubeSat development and then in high school science projects. So here, yeah.
Well, maybe you're getting to this, but one thing I noticed is that the soldering on that thing is so small. I don't know how anybody could do it without a binocular microscope.
Yeah, I am going to talk about that.
Okay.
So this was a microcontroller we developed in-house. We called them app boards. They were centered around a Texas Instruments MSP 430 microprocessor. The 430, it's a really good low-powered microprocessor. It gets used in industry a lot. It's good for satellite applications. It's good for battery-powered applications. We actually use them at my job at Sensys for some of our products. And this was easily, to this day, the most complex layout I've ever done. The traces here were very dense. There was a lot of components on this board. It was a 2-layer board. A lot of times for a board this dense, you'd go to like a 3 or a 4-layer board, and that way it's a lot easier to solve the routing problems of getting from one side to the other without hitting another wire. But we stayed with a 2-layer board for this. This was my first experience learning about what it takes to actually manufacture electronics. And like Doug was saying, there's a whole bunch of parts on this board that are surface mount that, I'm not a surface mount solderer. I could really not have much hope of assembling a board like this. So I had to learn about working with a contractor who could. I had to learn about working with the PC manufacturing houses that could do the higher density traces, because when we designed this board, the traces were closer together and physically smaller than what we had done on the previous boards, and that manufacturer couldn't handle them. And then there was, of course, the problems of managing a part supply chain, which are particularly relevant to me in my current job. So, finding that, parts were unavailable for some time on back order, deprecated, stuff like that, was a constant source of struggle. This is also where I had to learn about building assembly work instructions for those contractors so that I can describe to them what it is I want them to do, doing things like kitting up parts to send out so they can get assembled in return. And then finally, kind of a board tests phase where we do things like load on the bootloader and load on the virtual machine and confirm that this is a working board that's ready for us to start doing stuff with. So in learning by making, I did a lot of designing experiments like the one that you see here with this cool, this is like a jar full of mud that makes voltage, and we were measuring that. And I also did a lot of managing of the IT infrastructure, but that's kind of outside of the context of embedded systems. So the work done on this project was very much analogous to the work that was done by the designers of the Arduino or the Raspberry Pi, where we start with a microprocessor of some kind. We add in some useful components around it that are usually SMD. We bring out the pins from that microprocessor that we want to have access to the physical pins you see poking up there so that people can actually use them. Integrate devices like, in this case, a DAC and a timing crystal and resistors and such. And then we lay it all out, make sure that it fits and has the right tolerances, and finally we send it out, we have it built, we test it, and we make revisions as needed. Okay, so moving on to my first post-SSU example from this talk. This is a project I worked on that I just called the Pi Gateway. And with this particular project, the problem that I was trying to solve was that we had systems that were at our contract manufacturers, so kind of remote factories in the US and in China and in Mexico. And we wanted to be able to have reliable remote access to them, but they were always turning stuff off. So there'd be like a machine that had a static IP address that we'd want to remote into to be able to work on the machines there. And they'd call me up and say, hey, I need help. And then I'd call them back and say, hey, turn the machine on and I can talk to you. So we wanted to get around that. And the approach that I came up with was just taking a Raspberry Pi. And one of the advantages of the Raspberry Pi is that there's no off button. So to turn it off, you have to physically unplug it, and people are reluctant to do that. It's also really small, kind of low profile. I put it in that little black case so no one will really notice it. So in a lot of ways, I just kind of sneak them in there, and hopefully that no one touches anything. So this is an example of a pattern I like to call the headless server. It's just a Raspberry Pi and a network. There's no other devices involved in here, which is different from all the other examples I'll be giving. This is something that there's no applications for Arduino that work this way, where it's just an Arduino and nothing else for it to talk to. But the Raspberry Pi does have a few applications like this. Let's see. The Pis are really cheap. They're easy to ship, so I could just build one of these, put it in a box, send it to the factory. And then the Raspberry Pi obviously has the onboard Ethernet, which was useful for this because I don't have to worry about things like getting a wireless SSID or password or anything like that. Just plug it in and it's on the internet. And it uses an approach for communication called reverse SSH, which I learned about when I was here at Sonoma State and found super useful for this, where when the gateway gets connected to the internet, it automatically makes a connection back to a remote server that we control. And once that happens, then we can come in from a client anywhere else on the internet, connect to that same remote server, and we can follow the SSH tunnel that it makes back to the device. So this was super useful because I didn't have to do things like talk to IT people at these remote factories or get them to open up firewalls for me. It was just kind of fire and forget. Let's see. And then I also made a Python-based tool for navigating through this kind of an SSH environment. And that's something I'm currently trying to convince my work to let me open source. And so the moral of the story here is that open source software is important. I use it all the time. It's super valuable. And I am saying that it's okay to be an advocate for open source software at your job, and they try to get any companies you work for to contribute where they can. Okay, moving along. This is one of the more complicated projects that I've worked on. This was it's a mag sensor RF test chamber. So the problem that I was trying to solve here was that we had a testing approach for our sensors that was very manual, very time intensive, and so we wanted to automate it. And a lot of the work that I do is automating away manual procedures to save on cost, to make them more reliable, to get better data from them. So this test used an actual full-blown Linux computer, but it did have some embedded components I'm going to talk about, and those were implemented with an Arduino. And if you look along kind of the top shelf there, you see a whole bunch of little green squares. Each one of those is a PCB that I designed. We call them mag coil boards, but we affectionately refer to them as turntables, because if you look at the image right there, it looks kind of like a 45. If you don't get the reference, clearly I'm too old. And so this was an interesting project because this is a printed solenoid, basically, a printed magnetic coil. So if you look at the image on the right there, you see the red part's the top, and it kind of starts at the outside and it spirals in towards the inside. And then, let's see if I can get this. No, whatever. There is where it goes through a via, jumps to the back of the board, and then spirals back out again, and then finally completes the circuit. And so I was very skeptical this was going to work. I actually didn't think this would work. I just did it to get my boss off my back. But it actually did work. It worked just fine. So I was excited that everything came together on that one. Let's see. So we use the mag coils there. There's 16 of them. We put 16 sensors in here, and we can individually trigger them each to make sure that the magnetic sensors in them are working, and to test a few other things about the serial numbers. And then you can see that there's kind of a hinge there at the bottom, and this whole chamber closes. It's an RF chamber, so it has to have all the walls closed for it to really be isolating the devices. So I wanted to have a way that I could figure out whether or not the door is open. And I thought of a few different ways to do this. And I thought about like a contact sensor where it would touch when the door was closed. I thought about like a position sensor, potentiometer, that I could tell the angle the door was at. But ultimately the simplest solution I came up with, and if you look kind of right down here at the bottom, you can see a little tiny blue dot. And that's a light sensor, a really simple analog light sensor. So I just discovered like, hey, when the door's closed, it's pretty dark. And when the door's open, it's pretty bright. So it was really easy for me to use that to determine whether the doors are open or off. This example is a pattern I like to call the USB peripheral pattern, which means that the Arduino doesn't really do anything by itself. It's got a USB connection over that UART to the computer that runs all this. And it's just constantly listening for a special command of some kind. And this is kind of a language that you build up, or maybe a language isn't the right term, but just kind of a list of commands you build up that in this case it knows if you put a number and then on afterwards, then it'll turn that numbered solenoid switch on. Or if you say the command light to it, it'll return back to you the reading from the light sensor. So that's a really useful pattern whenever you have like an embedded device talking to either another embedded device or maybe a computer of some kind. And this was something that came to me from my work with Learning by Making, because when we did the work with the micro logo, that's kind of built into the way that micro logo was designed, where when you write code for a micro logo device, you can call those functions directly from the computer and it knows what you're talking about. So it's like it builds up that language for you automatically. Okay, so moving on to my last and favorite embedded project, and this is one that uses the Raspberry Pi. You can see a picture of it there. So the problem here was that we have a bunch of sensors that we're building, and we fill them up with this non-conducting material called potting, and that makes them resistant to water because we're going to be putting them in the ground and there's going to be lots of water. We want them to not die. And so the previous process of filling it up was pretty straightforward. Where we'd have just technicians with ketchup bottles full of this conductive material, and they'd squirt it in and they'd put it on top of a scale and they'd squirt it until they got the right value. And we decided that was a process that could be automated to save us on costs, to save us, to give us higher quality control, because we could tell the machine to fill to a much more exacting standard than we could expect a human to do it. And then it also gives us a whole bunch of more data about about each device, so I can look back now and tell you, to the 1/10 of a gram exactly how much potting material went into one specific sensor. So this was a Raspberry Pi powered device for potting. So of course I had to name it Barry Potter. This system was designed using Raspberry Pi. We've got a few high precision digital scales that communicate with that Raspberry Pi over serial. There's a pressurized system. You can see the controls port there on the left. That there's potting material under pressure. There's a set of solenoid switches above each scale that are controlled by the Raspberry Pi, and it can open and close them as it sees fit. And then in the back you see the monitor there. There's kind of some filling up graphics happening in this image, and that's also driven by the Raspberry Pi. So the Raspberry Pis can be useful for doing graphical user interfaces. And this is written in a language called Kiwi that I'm kind of lukewarm on, but it's a cross-platform, open source graphical user interface framework for Python. So the feedback algorithm that I used to accurately fill with potting material the sensors was something that I think warrants a little bit deeper of a dig. And this was something that actually Garrett helped me develop when we were working on Learning by Making, and we were originally using it for doing temperature regulation of those pots of mud that I showed you in the slide a few frames back. So in that example, we had a pot full of mud that was full of these bacteria, and we wanted to bring it up to a certain temperature. And because it was so well insulated, we really had to make sure that we didn't go over the temperature, because it wasn't going to come back down again particularly quickly. And that's really similar to the situation I had with the Barry Potter, where I'm filling it up with material and I don't have a mechanism to take material back out again particularly easy. So I want to make sure I never overfill. So the algorithm that I'm using here You can see on the graph here, I've got some data points that are filling in there just kind of randomly. And the blue dotted line represents a linear interpolation back through those points. The purple dotted line represents a linear interpolation forward in time. And then the red dotted line there kind of represents our target value. So the algorithm will turn off whatever the driving force is. So either turn off the flow of potting material in my case, or turn off the flow of heat into the system in the original case, if it projects that it's going to go over. Sometimes you'll get lucky, and that'll mean that it kind of coasts over the value you're looking for and lands right there in the sweet spot. Oftentimes it'll mean that you undershoot the target, and as you do that, it's continually checking what the last endpoints are. And as the slope decreases, eventually the projection will decrease until it's projecting that it won't go over the target again. And then it'll turn the flow of potting material or heat or whatever back on. And that's kind of a conservative approach to get you near the target in a series of steps without hopefully ever overshooting the target. So this algorithm had a couple of tuning factors that are useful to it. There's n, the number of points into the past that you consider. And then there's c, the number of time units into the future that you project. And you can use those to control how conservatively or how aggressively you approach the target. Okay. Finally, just shameless plug here. If you're interested in Arduino development, I've got some workshops that I do at 180 Studios. You can find the link there at the bottom. And that is the end of my talk. Thank you for your time.